Hello everyone, and thank you all for coming. My name is Kevin, and today we are, together with my team, I'm going to talk about the design of the new car that we're currently manufacturing. But first, I would like to see how many of you have heard about Formula Student before. So if you could please just higher your hand if ever. Perfect, thank you. Sorry. I often get the question, why are you in a Formula Student team? And I often respond by saying, because race car. I mean, it's not that plain if you think of it. The opportunity to design, manufacture, and actually compete with a Formula-style race car in multiple foreign countries. To implement smart solutions to a car that you somewhat heard of but never really fully understood. To actually start with a pen and paper and end up with a Formula-style race car that is faster than any four-wheel driven machine you've ever seen. It's pretty cool. Just as in any engineering project, the solution is only as good as the team behind it. With that said, I am glad to introduce the Chalmers Formula Student 2023 team. With a total of 40 project engineers in the team, we have 18 different areas of masters and more than 10 different nationalities in the team. In order to fully utilize every team member's skills, the team is divided into 7 different subgroups, each having their own responsibilities, closely working together towards a faster car. The team structure consists of a team director at the top, with the highest authority. Right under are the managers, who are responsible for each individual subgroup. The managers are selected students from the team director that were CFS members the former year. The project engineers, such as myself, are all placed under each subgroup and are students studying at the master's level. In addition to this, we also have trainees that voluntarily work towards a faster car and help us out a little bit. After more than 50,000 hours, more than 400 liters of coffee, and over 500 takeaway pizzas ordered from our formula room, we're proud to, for the very first time, present to you the design of our Chalmers Formula Student 2023 car. A four-wheel driven, fully electrical, both driveless and driver-suited Chalmers Formula Student car. Named after a former queen of Sweden and also a delicious pizza, we're glad to name this year's car Margareta. With a car this pretty, it is our responsibility to drive it at its greatest potential. That's why we're planning on going to not 2, but 3 competitions this summer. First up, with sharp corners and tough conditions, is the TT circuit Assen in the Netherlands. Followed up by the home of the Hungarian Formula 1 Grand Prix events and one of the largest Formula student competitions is the Hungary in Hungary. Then last but not least, against one of the most challenging uphill sections, the test track of Autodrome Most in the Czech Republic. The competitions are divided into separate demanding events, where points can be gathered for each successfully completed part. This is how the total amount of points is distributed. The car is tested on endurance, efficiency, acceleration, and its longitudinal and lateral capacities. There are also static events, where it is important to show that the car is not only fast, but also sustainable, appealing, and economical to manufacture. With that said, I think it is time to let some of the experts from manufacturing speak for themselves and present how their part is making Margareta as amazing as possible. First up is the subgroup Aero with Hjalmar. Welcome up.
Thank you, Kevin. Hello, my name is Hjalmar and I'm representing the Aerodynamics subgroup. So together with my subgroup, we have produced this year's aero package of the car, which you can see here. And to make a race car, one important factor is the car's grip. And that's where we come in with one simple word: downforce. Many of you may know, but downforce is the negative lift we can produce by using aerodynamical elements on the car to push the car down into the ground and thus increasing its grip and its cornering velocity, and increasing or decreasing lap time. I think we'll delve a bit deeper into the design, so we'll start off with the front wing. The front wing is a very crucial part of the aero package, as it produces a lot of downforce and provides grip for the front end of the car, so the front wheels. But it's also important to make a front wing that doesn't disturb the rest of the aero package behind it. So it's a hard thing to balance the performance of the individual part and the performance of the rest of the car. Secondly, we have our side structures. The side structures work as large expansion tunnels, which increase the velocity of the air and decreasing the pressure under the car and sucking it down to the ground. Then we have our diffuser. The diffuser works similarly to the side structures by expanding and making a low pressure zone under the car. And with this year's reintroduction of the aero step on the monocoque, we now have almost double the amount of downforce than we had last year's on the diffuser, which we are very happy with. Then lastly on the car, we have the rear wing. The rear wing on a Formula Student car is quite huge, because we have such a large volume to work with. And this year, this has always been completely revamped with a new main segment and new smaller flaps like the overwing and other stuff to increase its performance. And then our final aero package now. Yeah, I would just like to show you some of our improvements. So we have an increase in downforce from last year's car with 10%, with a CLA, a coefficient of lift times the area, of 4.9, which is very respectable. And we have also decreased the weight of the entire aero package to 9 kilograms, which we are very happy with. And with that, I would like to hand you over to Elin, who's going to talk about the frame of the car.
My name is Elin and I'm here to speak for frame today. This is the rest of this is the rest of the frame subgroup, and together we have designed these. In frame we work with the body of the car, the ergonomics of the driver and the safety for the driver. A big focus for us is the safety and of course the strength of the monocoque. We work a lot with packaging to make sure that everything that's supposed to fit in the car can actually fit in the car. We also do a lot with ergonomics this year to make sure the driver can drive as good as possible and perform as well as possible. The biggest part we have is the monocoque, which is the first thing we're going to talk about. Without it, it's very hard to assemble a car, so that's the biggest reason to make one. And we also, the big question is why make a monocoque instead of a tube frame? First, we gain a lot of design freedom in how we want to design the car. We also gain a lot of stiffness through the car, which is very important to transfer the loads from the rear to the front. The monocoque is made out of sandwich panels that are conducted out of carbon fiber and aluminium honeycomb core. From competitions, we have a lot of requirements on the material to make sure it's safe. These requirements are adapted to a steel tube frame. We do a lot of material testing on our materials to make sure that we can apply to the same requirements. The monocoque this year, we are trying to work with simpler shapes to make sure that it's easy to manufacture. We have worked with less carbon fiber to reduce the weight. Some of the features this year that we have introduced is the aerostep, which can be seen in the front floor of the car. We have also reduced or taken away the dashboard, which makes it a lot easier to manufacture, to take down manufacturing time. The dash will instead be attached later as a screen. Next up, we have ergonomics. That's something we worked a lot with this year, we focused a lot of our time on. This is very important for the driver to drive as good as possible. And for us, it's been a big iterative process. We made an ergonomics sheet where we could test all the possible solutions for the drivers to feel, what feels best for the driver. First, we have a seat. The seat supports the driver, the bottom part of the driver. We have paddings for the shoulders and legs to be able to take up the lateral loads for the driver. We have optimized the position of the steering wheel as well to make sure the driver has enough space to be able to turn the car well. Another thing that's very important is, of course, the safety. Safety is something we work with a lot, and it's a lot of requirements on the monocoque, and we have some parts that are designed purely for safety. First, we have the roll hoops. Those are made because the drivers to not be the highest point if the car gets turned upside down. In the front, we have an impact alternator and an anti-intrusion plate. This is in the case of a frontal crash that the car can pick up the load and nothing will penetrate the monocoque. We have firewalls, one behind the driver and one inside the monocoque to shield the driver from all the high voltage systems in the car. And all of this we do tests. We do tests on all the harness points to make sure that they can take enough load for it to be safe for the driver. And we also do a crash test to make sure that the impact alternator and the anti-intrusion plate can take up enough energy and force to make sure the driver can feel safe while driving the car. To sum this up, in frame, we have worked a lot with reducing weight, with design for manufacturability, and also the ergonomics of the driver. Next up, Powertrain is going to talk, and Jesper and Nilsson are going to present it.
Thank you, Elin. I am Jesper, and I'm here together with Nick to proudly represent the Powertrain subgroup of CFS23. And here we are. So, there we go. All right. So, what actually is the powertrain of the car? It is what stores and delivers the energy all the way out to the engines in order to make the car go forward, basically. And it looks something like this for Margarita. Okay, it consists of 4 major parts, and let's start at the core, which is the Tracted System Accumulator Container, or TSAC in short. It is what contains the battery, but also the management system of it. From there, the energy is fed forward to the power electronics, which converts the voltage from DC to AC and then feeds it forward all the way out to the engines or the electrical machines. And to keep all of this in its optimal state, we need a thermal management system as well, which keeps everything cool. It's a cooling system. Okay, so let's start by deep diving into the TSAC, and it looks something like this. There we go. All right. So this is what contains the actual energy in form of the battery. and the management system of it. And the box that you see right now is made out of aramid fiber reinforced polymer. And for you who don't know what that is, it's basically the same thing that they use in Kevlar for bulletproof vests and so on. And I'm not entirely sure, but I think that this box might actually be bulletproof as well. So that's kind of cool. We haven't tested it though. But why are we actually using this material? It has a lot of good benefits, and it is fireproof, it is non-conductive, and as I said, it can take a lot of load. And why we need that is because of the batteries, kind of a very dangerous part of the car. So we don't want anything to happen to it, even in the scenario of a crash or so on. So we need to make sure that it's always protected from the driver and from everyone around the car. And inside, it looks something like this. So in the back there, you can see the 6 grey segments, which are compartments of the energy, basically. And in the front, where you see the PCBs, that is the relay box, the management system of it. And to jump even further in, this is the just the accumulator part of it. And for this year, it is totally redesigned because the team are acquiring new battery cells that are a lot improved from last year. And while designing this battery, there were kind of 3 main parts that we aimed for, which was simplicity, safety, and modularity. And the reason behind that was to make it very easy to work with and to be safe, since it's 600 volts in total. It's very dangerous to touch in the wrong way, and it can catch fire and so on. So we want it to be as easy as possible to work with in order to make as few mistakes as we can. All right. So it consists out of 6 segments, as I said. Together they are series connected and make up a peak voltage of around 600 and a capacity of 13 amp hours, which we can deliver all the way out into the car. And the main change of the new cells that we acquired is basically that the peak recharge rate of the cells is almost 10 times as much as last year. What that means is that we can regen a lot more energy while driving by spinning the motors backward, for instance, when we are braking the car. And in the long run, that means that, for example, the endurance event, which is the longest event that we drive in during competitions, during that we can push more power out to the motors and drive faster without actually emptying the battery, since we can regen so much while driving as well. And that in the end scores us more points, and of course that is what wins the competition. So hopefully that's something that's going to happen this year. Each segment that you see, they are air-cooled, and each of them have a separate air cooling system. The reason for not having a common system is because the rules kind of makes that impossible. And speaking of the segments, they look something like this while assembled. And it's basically just a block of 23 cells that are connected. And here's an explosion view of it. And the main part is, of course, the cells, which you see in grey. And on top of them, you can see 2 PCBs, which are the carrier board and an AMS follower. And the reason why they are there is just to make sure that the cells are connected in the correct way, and also to make sure that we can measure such as cell voltage and cell temperature and so on of everything, to keep everything in a good state. And the rest that you see around it is just a 3D printed fireproof material kind of casing that is there to redirect any loads that are coming onto the battery to make sure that it's as safe as possible. So the car consists and has a lot of energy in it. But how do we use this and how do we control it now?
Very good question, Jesper. Since we redesigned the battery for this year, we also redesigned the relay part of the battery. So the front part of the battery you can see in front here. What is the relay box? Why do we need it? So, like the name said, the relay box contains the relays. So the relays enable us to disconnect and connect the car to the battery. So enables us to connect a 600 volts DC battery we have, Jesper said, to the vehicle side of our car. Besides the relay box, the relays in the relay carrier, we have more PCBs, of course, in it. One of them is the AMS master. So we monitor every segment, we monitor every voltage of every segment, thus we can calculate every SLC level of every segment. So, Further on, we have 2 more PCBs, the AIL and the TSAL. These are 2 PCBs only there to see if the car is actually safe. So it makes, it shows us if the car is ready to drive and if the car is connected to high voltage or not. But the
the most important PCBs you can see here, these two. These are our DC-DC converters 1 and 2. So we are one of the few teams in Formula Student which does not have one single low voltage battery. We rather have one big high voltage battery and convert our high voltage battery or our high voltage to low voltage. So instead of having 2 batteries, we have 1 battery and low voltage converters. So after we connect our battery to the relays, we can transmit our high voltage afterwards to our PE box. The PE box is basically a box which contains our 4 inverters. So we have 1 inverter for each motor. We have 4 motors in total, and it's basically a carryover from last year. What we have modified this year, however, is the mounting of the PE box and also the packaging of the PE box. So what we have is data loggers now, which are which have a higher frequency of sampling, and we can thus increase our information we gain from our battery. After we convert in the PE box our DC current to AC current, or DC to AC, it gets feed to our motors. Our motors are also completely like a complete carryover from last year, but we designed the motors as well as the gearbox and the cooling. So we have an additive manufactured cooling jacket which cools our motors and keeps it at an optimal temperature. And talking about cooling, this year we also improved our cooling system by having new radiators which are more efficient, way less, and thus we can have less water in the system and cool our battery and our motors even more efficient. So this together makes the whole powertrain this year more efficient, more durable, and probably way faster. So we as NPT deliver the energy from the battery to the motors and then to the wheels. That's our task. Then suspension comes in with Zakari and tries to put the power we gave them to the ground.
Thank you. Hi, so I'm Zakari. I'm part of suspension, and along with these other project engineers and training we have, we work together to develop the CFS23 suspension. So I'll show you the first look at it. This is the overall system. These are all the components we are in charge of. That includes the linkages, the steering system, the braking system, the actuation, and part of the wheel package. One of our main roles is to actually make sure that only the tires are the only part that touches the ground. We're also in charge of the overall handling characteristics and how the vehicle reacts to the road inputs. I will showcase the main component that helps with the road input, and that is the actuation. This year we have reworked the overall actuation system. In the front actuation system, we have a direct actuation with coupled heave and roll motion. This here is quite simple by having the damper directly connected to the wheel package. Next, in the rear, it's more complex. We decided to go with a anti-roll bar to be able to adjust the stiffness and the overall roll distribution. We also have a belt crank system where we can control the motion ratio by how it's connected to the wheel package. We also have dampers which allow a huge range of tunability by having different and independent low speed and high speed compression and rebound damping coefficients. Next, one of the ways we managed to achieve the 10% weight decrease that I showed in the first slide is by having a method of design which allows us to have a topology optimized parts. Those parts are more organic and they follow the load path that they are actually subjected to. And that allows us to minimize the mass with the required stiffnesses. Some of the parts are the wishbone bracket, which is the part that connects the linkages to the vehicle and the wheel package. Next, we have the upright. So this is where we have the connection between the powertrain, where the drivetrain is connected to the suspension system. And next is the steering bracket. which is how we hold our steering column to the frame. We're also in charge of the braking system and the pedal box. So this year's pedal box has completely been reworked with a new design. It has to be adjustable for a different class of drivers, but it has to accommodate as well for autonomous system. So it has to incorporate both hydraulic braking system that is used for driver and the pneumatic actuators which are used to brake for the autonomous system. The actuators can be seen in the back of the pedals. This year, we have improved greatly the ergonomics and how we are able to adjust it. I will now let Amandus present for the electronics.
Thank you, Zakari. All right, so my name is Amandus, and I'm a part of the electronics subgroup, together with my co-workers up here. And in the electronics subgroup, we are divided into 3 different subdomains, or 3 different areas, which are hardware, software, and control systems. And I'm going to briefly introduce the different subgroups, as well as what we are currently working on in this year's iteration of the car. So, to get started, this is the main low voltage skeleton of the car, and the hardware group does the main job of connecting all the different systems and sensors together. We have multiple CAN lines running through the car. We have a LiDAR, a driverless computer, as well as a remote emergency brake system. And these systems are impressive on their own, but they need to be able to communicate very efficiently to be able to extract their full potential. That's why another part of the hardware group is designing our own PCBs, our own printed circuit boards that look something like this. By designing them ourselves, we gain the advantage of being able to adapt them to our very own needs and wants. And yes, and for this year, we have worked very hard to streamline the entire electronic system. We have removed several microcontrol units and combined other components together onto singular printed circuit boards. And this will hopefully make for a car that is easier to manufacture and to do maintenance on. And next up is the software. So the software, they use these microcontrol units and to be able to make informed decisions. And to borrow one of the older sayings, is that the software is the brains that use the network made by the hardware to make informed decisions. Due to the reduction of the nodes and the combination of other PCBs, we have been forced to restructure the code a bit to fit the new layout a bit better. And we are also working hard on enhancing the driver-to-car interface so that more relevant information is displayed to the car, to the driver during runs, and so that the driver can also make some small adjustments during the run. Lastly, we have the control systems. And the control system's main goal is to make the car utilize the systems it has in the most efficient way possible. This involves mainly monitoring battery and motor usage. For this year, one of the things we're working on is a more efficient power limiter. The goal of the power limiter is to make sure that we draw as much power from the accumulator as possible, whilst still complying to the rules of the competition. There's a limit on how much average power we can draw from the accumulator, so we want to make sure that we are close to the border, but not quite above it. And this is achieved by monitoring it closely and regulating. Another thing that the control system group is working on is torque vectoring. And torque vectoring is distributing the available torque optimally to the different motors to make sure that we align the actual acceleration with the desired acceleration to make the car run in the way that we want. And to wrap up, all of the control systems use software and calculations to make sure that we utilize the systems optimally, because otherwise we could just as easily have worse components if we're not using them properly. And this has been all for me, so I'm going to hand it over to the autonomous group and Anton.
Thank you very much, Amandus. So, hello, my name is Anton, and I will be representing the autonomous subgroup. So, when you think about an autonomous system, you mostly think about the software. But there are a few key hardware components that enable the car to drive autonomously. The first one of these is the LiDAR sensor, which enables the car to see the world. We have once again opted to go for a LiDAR-only system this year due to its reduced complexity, its fast computation times, and its far detection range. Besides being able to see, we also want to know where we are and how fast we're going. This is where our high precision IMU sensor comes in, which combines accelerometer and gyroscope measurements together with satellite tracking to give us centimeter level precision, both in position and in velocity. But knowing the environment is not everything. We also need to be able to interface with the car to make it go forwards. So for steering, we are using a small form factor pancake motor. For throttle, we can simply send commands to the power electronics. And for braking, we can utilize the region that Jesper talked about, as well as the pneumatic actuators that Zakari mentioned earlier. Not pictured here is the driveless computer, which ties everything together. It collects all the information from the sensors, processes it, and sends the appropriate commands to all of our motors. This brings us over to the software part. So we are running a ROS2 based system where we have so-called nodes running in Dockerized containers. This allows us to manage our very large code base in a nice way and allows us for some modularity in our system. So the first one of these nodes is the perception node, which handles the point cloud data that we get from the LiDAR and processes this from raw points into the cones that make up the track. So a short run-through of this process is that we first take the raw points, we detect the ground, we remove the ground, perform clustering on the remaining points, we then reconstruct the cones, and then try to validate and see that there actually are cones. This entire process we're able to do in less than 5 milliseconds, which is very, very fast. The cones that we get from the LiDAR are in the local frame of view of the car. To be able to save this in a sort of global map, we use a graph-based SLAM algorithm, which associates the newly seen cones with the ones that are already in the map and continuously optimizes over this graph to get a consistent map as well as the car's position within that map. When we have the entire track, we can plan the path that we want to go. So we then plan for the center line of the path and use our control algorithms to follow that as closely as possible. So we are using a decoupled longitudinal and lateral controller, which allows us for a lot of flexibility in the way we tune the steering and the throttle. To show all of this in action, we have a short video which visualizes what the autonomous car sees and how it drives. So this is real-time data from one of the testing sessions we did during the fall. What you're seeing is the raw point cloud that we get from the LiDAR aggregated in the global map of our SLAM algorithm. And here you can see it in the map frame of view. So with the point cloud, we first remove the ground and then perform the filtering to get only the cones. These cones are then stored in our global map, and we plan the perfect path to go through the track, which we are then following with our control algorithms. All of this tied together leads with a consistent track and a car that can move through the track with precision. And that is all for me. And I will now hand the torch back to Kevin, who will say some final nice words.
Thank you for all the technical presentations. Together we work efficiently and sharply towards a faster and more functioning car. With a lighter and more tested Formula Student car, we aim to have Margareta fully manufactured and ready to drive by the end of May. With a larger Chalmers Formula Student team, we aim for the top 5 in all competitions. None of this would have been possible if it weren't for our sponsors. So a special thanks to Volvo Cars, Aros Electronics, ESIC, Chalmers, and to everyone that is here today and has listened to the presentation. If you have any further questions or want to know more about the car, please come meet me and the rest of the team outside of the lecture hall to have a chat and grab some fika. Chalmers Formula student. We deliver the engineers of tomorrow. Thank you.
Av våra